At 1:36 in the morning, Universal Time, the Sun fired the third largest flare any sunspot region produced this year. 5 hours later, it fired again. 5 hours after that, the third one, an X-class event that triggered an R3 radio blackout across the sunlit side of Earth. All three came from one patch of solar surface, just past the central meridian, on the most geo-effective real estate the visible disk offers. Two of those flares launched coronal mass ejections that two independent spacecraft have now confirmed are headed directly toward our planet. Tonight, we walk through everything that just happened, everything that is in transit, and the single variable that determines whether the next 48 hours produce a storm or pass in silence. If you want to know the moment this develops, hit subscribe, drop a comment with where you're watching from, and whether the aurora has reached your latitude tonight. Now, let's get into it. At 1:36 in the morning, Universal Time on June 3rd, 2026, the Sun fired. Not a regular flare. An M9.3. An X-ray event that came within a hair of crossing the threshold into X-class territory, the line that separates strong from extreme on a scale that runs from background C-class noise all the way up to the kind of events that knocked telegraph systems off the wires in the 19th century. M9.3 is the upper edge of the second strongest class, the kind of event that, on its own, would have been the lead story of the morning for anyone who follows space weather. But it was not on its own. 5 hours and 24 minutes later, at 7 in the morning Universal Time, the same patch of solar surface fired again. An M7.7. Another upper-end M-class event from the same active region, the same magnetic complex, the same square of sunspot territory rotating across the face of the sun. And then, 4 hours and 28 minutes after that, at 11:28 in the morning Universal Time, the third one came. An X1.0. The threshold crossed. The first X-class event of this active period, a strong-rated radio blackout, the kind of event that NOAA labels with the all-caps R3 classification on its space weather scale, and sends out as an immediate alert to power grid operators, satellite operators, and the half a dozen agencies that have to know within minutes whenever the sun does something that can interfere with terrestrial communications. 3 major flares, 10 hours, 1 region. The region in question has a number. NOAA active region 4455. The number itself does not mean very much to most people, which is part of why this story is so easy to miss. But the location does. 4455 sits at solar coordinates north 14, west 20. Translated into plain English, that puts the region just past the central meridian of the sun, on the Earth-facing hemisphere, slightly past the point that points directly at us. From Earth's perspective, this is the most geo-effective real estate on the entire visible solar disk. Anything that the region launches into space has the geometric setup to travel along a path that intersects with the planet. You should remember the location, because the next time someone tells you that the events of June 3rd did not affect Earth, the location is the first thing you check. 4455 fired straight at us. There was a warning before the cascade. At 16:50 Universal Time on June 2nd, the afternoon of the day before, region 4455 produced an M3.3 flare, mid-range M-class. Worth noting, not worth alarm. The region was awake. The region was active. The region had something to say. But an M3.3 on its own gets cataloged and filed and moved past, which is what happened. What did not get filed and moved past was the size and the configuration of the region itself. 4455 had an area of 330 millionths of the solar hemisphere, large, firmly in the upper range of active regions in the current cycle. 17 sunspots inside it. A CME classification that puts it in the second largest size category for sunspot complexes. and a magnetic classification that anyone who watches space weather should learn to recognize when they see it. Beta gamma, with anti-hail geometry. We will come back to what that means. For now, what you need to know is that beta gamma anti-hail is one of the most flare-productive magnetic configurations a sunspot region can have, and 4455 had it all on display, all at once. That is the setup. Now let's talk about what the flares actually did. The M9.3 at 1:36 in the morning. Universal time did not just produce an X-ray spike. It produced a Type 4 radio sweep, a broadband radio emission that signals a sustained release of accelerated electrons in the solar corona. It produced a 10.7 centimeter radio burst that peaked at 360 solar flux units. For context, the background level for that wavelength on a typical day right now is around 146 solar flux units. This single event tripled the background brightness of the sun at that wavelength for the duration of its peak. A major energy release with a significant particle acceleration component. The M7.7 at 7 in the morning. Universal time produced something even more striking. The 10.7 centimeter radio burst peaked at 540 solar flux units, substantially higher than the M9.3 event that preceded it, even though the X-ray classification was technically smaller. The 540 unit burst also carried what is called a Castelli U signature, a specific U shape in the radio frequency spectrum that experienced observers know to look for, and when they see it, they sit up. The M7.7 also produced a Type 2 radio burst with an estimated shock velocity of 313 kilometers per second. A Type 2 burst is the radio fingerprint of a shock wave moving outward from the sun through the corona, the wavefront driven ahead of a coronal mass ejection as it accelerates away from the surface. 313 kilometers per second is the shock speed, not the eventual interplanetary speed, but it tells you that this event launched material outward fast enough to drive a detectable shock. And then, the X1.0 at 11:28. The third flare in the cascade. The 10.7 centimeter burst from this one peaked at only 250 solar flux units, notably lower than the two flares before it, which is one of the most interesting details in the entire dataset, and one we will come back to. The X-class classification triggered NOAA's standardized R3 radio blackout warning. R3 means a wide area blackout of high-frequency radio communication on the sunlit side of Earth for approximately an hour, and lower frequency degradation that can persist longer. Anybody trying to use HF radio in the Atlantic Basin, or over Europe at the moment, that X1.0 peaked, experienced the effect directly. There is one more detail that NOAA explicitly included in its alert text for the X1.0. The official summary noted that GOES-18, the primary satellite that NOAA uses for X-ray monitoring of the sun, was in an outage at the moment of the X1.0 peak. So NOAA used GOES-19 instead. The X-ray classification is the same. GOES-18 and GOES-19 carry near-identical X-ray sensors, routinely cross-calibrated. The R3 classification is robust. The disclosure is not a cover-up. It is the opposite of a cover-up. It is NOAA telling you, in plain text in the public alert, exactly which sensor measured the event and why, which raises the question, if NOAA is being this transparent about the measurement itself, why does its forecast for the next 3 days still predict geomagnetic quiet? That is the central question of this video. Because while we were watching 3 flares fire in 10 hours, 2 clouds of plasma the size of planets were already launching toward Earth, and a third one might be on its way behind them. The flares are the visible part of the story. The plasma clouds are the part that actually matters for Earth. When the M9.3 peaked at 1:36 in the morning Universal Time, the X-rays from that event reached Earth 8 minutes later. Because X-rays travel at the speed of light, and the sun is approximately 8 light minutes away. By 8 minutes past 2 in the morning, Universal Time, the X-ray spike was over. The radio blackout that the flare produced on the sunlit side of Earth was already in progress, and the orbiting coronagraphs that watch the solar atmosphere were already turning their attention to the question that the flare itself only previewed. What did it launch? The answer came at 13 minutes past 2 in the morning, Universal Time, when the SOHO satellite's LASCO C2 coronagraph, an instrument that uses an artificial occulting disk to block out the bright face of the sun and image the much fainter outer atmosphere around it, caught the first frame of a coronal mass ejection emerging from the solar limb. The structure was faint. That word, faint, appears in the NOAA Space Weather Prediction Center discussion text describing this event, and it is worth taking seriously, because a faint CME is harder to characterize than a bright one, and the propagation modeling carries elevated uncertainty as a result. But the structure was visible. It was there. The GOES SUVI imagery, extreme ultraviolet observations from a different vantage point, suggested that the CME structure was a partial to full halo. A halo CME is one that is moving more or less directly toward or away from the observer, so that its expanding cone of plasma appears to spread out evenly in all directions from the central source. From Earth's perspective, a halo CME from a region on the Earth-facing hemisphere is the geometric signature of an Earth-directed event. NOAA triangulated the imagery from SOHO with imagery from Stereo, a separate spacecraft that views the sun from a different angle, and concluded that an Earth-directed component is present. Let that sink in. The M9.3 flare launched a coronal mass ejection. The CME has been confirmed by 2 independent spacecraft from 2 different viewing angles. The structure is faint, which means the precise speed and density are harder to pin down than a bright event would be. But the Earth-directed component is confirmed. A cloud of magnetized plasma, billions of tons of solar atmosphere torn loose and accelerated to interplanetary speeds, is at this moment in transit toward our planet. And then, less than 6 hours later, the M7.7 launched a second one. LASCO C2 caught the M7.7 CME at 48 minutes past 7 in the morning Universal Time. Both the coronagraph imagery and the SUVI imagery suggested that the bulk of this ejecta was deflected northward, pushed off its initial trajectory by interaction with a nearby coronal hole. Coronal holes are regions of the solar corona where the magnetic field lines are open rather than closed, allowing high-speed solar wind to stream outward unimpeded. Open magnetic flux from a coronal hole can torque a passing CME, pushing the cloud off its launch trajectory by tens of degrees. The northward deflection of the M7.7 CME is, by NOAA's own observation, significant enough to mention explicitly in the discussion text. But the deflection does not eliminate the Earth-directed component. Stereo triangulation confirmed that even with the northward push from the coronal hole, the M7.7 CME still has an Earth-directed component. The eastern flank of the cloud is still on a trajectory that intersects with Earth's orbital position. It may not be a direct frontal hit. It may be a glancing blow on the side of the cloud rather than the dense central core. But the cloud is, in part, headed our way. And there may be a third one. The X 1.0 at 11:28 in the morning Universal Time has not, as of the NOAA discussion text I am working from, produced confirmed coronagraph imagery of an associated CME. The agency's published text simply says that if a CME is associated with this flare, it should become visible in coronagraph imagery in a few hours. By the time you are watching this video, the question of whether the X 1.0 launched a third CME may already be resolved. As of midday on June 3rd, it was still open. There is one detail about the X 1.0 that gives observers some cause for cautious interpretation, and it brings us back to that 10.7 centimeter radio burst peak I flagged earlier. The X 1.0 produced a burst of 250 solar flux units. Compare that to the 360 from the M9.3 and the 540 from the M7.7. The X1.0's burst was smaller. The radio burst at 10.7 centimeters is a rough proxy for the acceleration of energetic particles into the corona, and the smaller burst correlates with less particle acceleration, which can correlate with reduced CME mass and velocity. If a CME is associated with the X1.0, it may be slower and less dense than the two events that preceded it. The coronagraph imagery, when it resolves, will give the definitive answer. Now let's talk about what these CMEs actually are. A coronal mass ejection is a cloud of magnetized plasma, ionized gas threaded with magnetic field, that gets ejected from the solar corona during an eruption. A typical CME contains between 1 billion and 10 billion tons of material. That is not a metaphor. That is the actual mass. The cloud expands as it travels outward, forming a roughly cone-shaped structure that propagates through the inner solar system at speeds that can range from a few hundred kilometers per second to over 2,000 kilometers per second in extreme events. At the lower end of the speed range, transit time from the Sun to Earth, a distance of approximately 149 million kilometers, one astronomical unit, is on the order of 3 to 4 days. At the upper end, transit time can be as short as 15 to 20 hours. The Type 2 shock velocity for the M7.7 was 313 kilometers per second. That is on the slower end of the CME velocity range. At that speed, the M7.7 CME would take approximately 2.5 to 3 days to reach Earth, putting arrival sometime in the June 5th to June 6th window. The M9.3 CME's velocity is less precisely characterized because the structure was faint, but the typical velocity range for halo CMEs from M-class events places it in a similar transit window. That means the two confirmed Earth-directed CMEs are arriving inside a window of approximately the same 48 hours. They may stack on each other in transit. They may arrive close enough together that the second cloud is still embedded in the wake of the first. And the geometry of CME interactions in the inner heliosphere is one of the most complicated problems in space weather modeling. But there is something else already in the inner heliosphere that nobody talked about for 9 hours after it left the Sun. Something moving more slowly than these CMEs are catching up to it. Something that the two confirmed Earth-directed CMEs are on a collision course with. On June 2nd, the day before the cascade began, a large filament eruption occurred on the southwest portion of the visible solar disk. A filament, in solar terminology, is a structure of dense, relatively cool plasma suspended above the solar surface by magnetic fields. When a filament destabilizes and erupts, the suspended plasma is launched outward, creating a coronal mass ejection. The June 2nd filament eruption was modeled, and the modeling confirmed that its CME has no Earth-directed component. The ejecta launched away from Earth's geometric line of sight. By itself, this event would not have generated any Earth arrival concern. But the filament's CME is not by itself anymore. It is in the inner heliosphere, traveling outward on a trajectory that does not directly intersect with Earth, but that is slower than the CMEs that have launched behind it. The two confirmed Earth-directed CMEs from June 3rd are both faster than the June 2nd filament eruption. They will catch up to it, and when they catch up to it, they will interact with it. The NOAA Space Weather Prediction Center discussion text, the official, publicly available analytical product that the agency releases for forecasters and infrastructure operators, explicitly says this. Verbatim, the discussion notes that the filament eruption has a high probability of interacting with the faster CMEs behind it and changing their propagation into the near-Earth environment. I want you to hear that sentence again, because I cannot overstate how unusual it is for an operational space weather forecast product to flag inner heliosphere interaction risk in this direct language. Forecasters usually keep their analytical text focused on the most likely outcome. When the NOAA writers go out of their way to name a specific physical interaction that will modify the propagation of an arriving event in ways the models cannot fully resolve, they are telling you that the agency itself is treating arrival time and arrival geometry as carrying elevated uncertainty. They are signaling in operational language that the forecast you see is being constructed on top of a known modeling gap. What does CME on CME interaction actually do? When a faster CME catches up to a slower one in the inner heliosphere, the faster cloud compresses against the back of the slower one, increasing the local plasma density at the interaction region. The magnetic fields embedded in both clouds get squeezed and restructured. Depending on the orientation of the fields, this can either reinforce a coherent magnetic geometry or create a tangled, chaotic field structure. The kinetic energy of the trailing CME pushes the leading CME forward, accelerating the combined disturbance and reducing total transit time. And the leading CME effectively clears a channel through the ambient solar wind, reducing drag on the trailing event. The net result is that a CME on CME interaction typically produces an arriving disturbance at Earth that is faster than the average of the two CMEs would predict, denser than the trailing CME would have been on its own, and more magnetically complex than either cloud individually. The interaction can amplify the disturbance's geomagnetic impact, or it can scatter the disturbance in a way that reduces its impact. Which outcome occurs depends on the specific geometry, which depends on the relative trajectories and magnetic orientations of the clouds, which are not precisely measurable from solar observations alone. This is the modeling problem that NOAA explicitly flagged. The June 2nd filament eruption, the M9.3 CME, and the M7.7 CME are now three objects in the inner heliosphere on overlapping trajectories. They will interact. The arriving disturbance at Earth, when it gets here, will not be a simple summation of three independent CMEs. And while all of this is in transit, the forecast that the public sees says no G1 or greater geomagnetic storming is expected through June 5th. I am not making that up. The official 3-day forecast from the NOAA Space Weather Prediction Center, issued at 12:30 Universal Time on June 3rd, after the M9.3 and the M7.7, before the X1.0 impact was reflected, predicts a peak KP of 3.67 through the forecast window. KP 3.67 is below the threshold for G1 minor geomagnetic storming, which begins at KP 5. The forecast predicts quiet. The forecast predicts no aurora alert. The forecast predicts no infrastructure heads up. The forecast predicts that the next 48 hours will be operationally indistinguishable from a normal mid-cycle background period. That is the public-facing product. That is what infrastructure operators and the general public are working from. And it contains the same agency, in the same hour, telling you that three objects are interacting in the inner heliosphere in ways the models cannot fully resolve. How do you reconcile these two things? That is the question I want you to hold in your head for the next 3 parts of this video. Because the answer is not that NOAA is hiding the real forecast. The answer is not that there is a secret prediction the agency is sitting on. The answer is something more interesting and more uncomfortable, and it has to do with what a space weather forecast actually claims, and what most people assume it claims, and the gap between those two things that almost nobody is taught to read. To get to the answer, you have to understand the region that fired. You have to understand the variable that decides the outcome. And you have to understand why every conspiracy framing that tries to fill the gap between dramatic events and a quiet forecast collapses on its own logic when you actually look at the mechanism. Let's start with Region 4, 455. Region 4, 455 was not a random sunspot complex that happened to fire 3 times in a row. It was a specific magnetic configuration with specific physical properties, and the configuration is what made the cascade possible. I told you earlier that the region had a CME sunspot classification and a beta-gamma magnetic class with anti-hail geometry. Let me unpack what those terms actually mean. Sunspot classification on the modified Zurich scale runs from A through H, where A is a small unipolar spot and H is a large, complex magnetic structure with multiple umbrae. The CME designation places region 4455 in the C range. Bipolar groups with sunspots of significant size and complexity. CME means a moderately large bipolar group with substantial structure. It is not the largest possible sunspot complex, but it is firmly above the threshold where significant flare productivity becomes likely. The magnetic classification is the more important part. Solar physicists use a system developed by Mount Wilson Observatory to categorize sunspot groups. Alpha is a single dominant polarity. Beta is a bipolar configuration with positive and negative polarities clearly separated. Gamma is a complex configuration where polarities are mixed in an irregular way. Delta is the most extreme, opposite polarities within the same penumbra. Beta gamma, which is what region 4455 was classified as, is a hybrid, a generally bipolar structure with localized regions where the polarities are mixed. Why does this matter? Because magnetic reconnection, the physical process that releases the energy stored in solar magnetic fields and powers flares, is most efficient in regions where opposite polarities are in close proximity to each other. A clean bipolar region with positive on one side and negative on the other has a single boundary between polarities, called the polarity inversion line. A beta-gamma region has multiple polarity inversion lines, each one a potential site for reconnection. A delta region has polarity inversions inside individual penumbra, which is the most magnetically stressed geometry a sunspot complex can have. Region 4455 was beta-gamma, not delta. But here is where the anti-hail geometry comes in, and this is the detail that elevates 4455 from active region to exceptional flare producer. Hale's law is one of the foundational regularities in solar physics. The astronomer George Ellery Hale, working at Mount Wilson in the early 20th century, discovered that the polarity arrangement of bipolar sunspot groups follows a predictable pattern across a solar cycle. In any given cycle, in any given solar hemisphere, the leading polarity, the spot that is rotationally ahead of the trailing spot as the sun rotates, has a specific magnetic polarity. The trailing spot has the opposite polarity. This rule holds for the vast majority of sunspot groups in a cycle. The exact polarity assignments flip from one cycle to the next, but the rule itself is consistent. Leading polarity is one sign. Trailing polarity is the other. When a sunspot group violates this rule, when the leading polarity is the wrong sign for its hemisphere and cycle, the group is called anti-hail. Anti-hail regions are statistically rare. They make up something like 3 to 5% of sunspot groups in a typical cycle, and they are disproportionately flare productive because the polarity inversion line in an anti-hail region runs against the prevailing magnetic flow of the global solar field, creating additional shear and stress. Region 4455 exhibited anti-hail character. The NOAA discussion text specifically notes that the region had a series of small negative polarity spots developing south and west of its mature positive polarity main spot. This is the anti-hail signature, the polarity arrangement that runs against the expected configuration for the hemisphere and cycle. Continuous flux emergence was also noted. Flux emergence is the process by which new magnetic field rises up through the solar surface from below, adding fresh magnetic energy to a region. When flux is emerging continuously, and that flux is interacting with an existing complex magnetic structure, the region is being actively fed energy. The mixed polarity geometry, plus the continuous flux emergence, plus the anti-hail character, plus the beta-gamma classification, plus the 17 sunspots, plus the 330 millionths area. That is the combination that produced 3 major flares in 10 hours. You can verify the importance of this combination by looking at the other active regions on the Earth-facing disk on June 3rd. Region 4, 458 at South 5, West 8. Region 4459 at North 14, East 35. Region 4461 at South 20, East 57. Region 4462 at North 17, East 59. 3 of those 4 regions developed gamma magnetic configurations during the same reporting period due to rapid flux emergence. They had the magnetic complexity, they had the active development, and they stayed flare quiet. Region 4460 at South 22, West 74, with a Dow classification and a beta-only magnetic class, also stayed quiet. Why did 4455 fire and the others not? Configuration is necessary, but not sufficient. Region 4455 had the configuration and the trigger. The others had the configuration and were waiting. They may yet fire. The NOAA forecast continues to give M-class probability to multiple of these regions over the coming days. But the convergence of factors that produced today's cascade was specific to 4455. This connects back to the central thread of this video in a direct way. 3 flares from one region in 10 hours is not random. It is not unprecedented. It is not the signature of some external intervention or hidden mechanism. It is the consequence of a magnetic configuration that almost never appears, firing in the direction of Earth during a phase of the solar cycle when large complex active regions are at their most common. The cascade had a physical cause. The physical cause produced the events. The events produced the CMEs, and the CMEs are in transit. Now, we have to talk about the variable that decides whether those CMEs do anything when they get here. There is a single variable that decides whether a coronal mass ejection produces a geomagnetic storm at Earth. That variable is the orientation of the embedded magnetic field within the CME at the moment it arrives. Solar physicists and forecasters call it Bs. Earth has a magnetic field that, at the boundary between near-Earth space and the solar wind, a region called the magnetopause, points generally northward. The solar wind that flows past Earth at all times also carries a magnetic field embedded in the plasma. When the solar wind's embedded field also points northward at the magnetopause, the 2 fields are aligned, and they push against each other without much energy exchange. Earth's magnetic shield holds. The plasma flows around. When the solar wind's field points southward at the magnetopause, the 2 fields are anti-aligned. They reconnect. Magnetic field lines from the Sun and from Earth break and reconnect across the boundary. Energy stored in the magnetic configuration gets converted into plasma motion and particle acceleration. The reconnection opens channels for solar wind plasma to penetrate Earth's magnetosphere. The energy that enters is dissipated through particle precipitation into the upper atmosphere, electrojet currents in the ionosphere, induced ground currents in the long conductors of the planet's surface. The visible signature is the aurora. The infrastructure signature is the geomagnetic storm. Northward BZ means alignment, means quiet, means no storm. Southward Bs means anti-alignment, means reconnection, means storm. The size of the storm depends on how strongly southward the BZ is and how long the orientation persists. For a coronal mass ejection arriving at Earth, the BZ orientation is set by the magnetic geometry of the CME itself. A CME is essentially a chunk of solar atmosphere, with its magnetic field carried along inside it. The field inside the CME can be oriented in any direction, and as the CME rotates and deforms during its propagation through the inner heliosphere, the embedded field orientation evolves. When the leading edge of the CME crosses the L1 Lagrange point, a stable gravitational position approximately 1.5 million kilometers earthward of the Sun, where the DSCO VR and AC spacecraft monitor the inbound solar wind, the embedded field can be measured directly for the first time. That measurement gives forecasters approximately 15 to 60 minutes of warning, depending on the speed of the CME before the disturbance reaches Earth. 15 to 60 minutes. That is the operational window in which the decisive variable for storm severity becomes knowable. Before L1, BZ cannot be predicted with confidence. Solar observations of the CME at its source tell you something about the initial geometry, but the field gets restructured during propagation. Interactions with the ambient solar wind, interactions with other CMEs, interactions with structures like the June 2nd filament eruption, all of these can rotate, compress, or scramble the embedded magnetic field in ways that current models cannot precisely simulate. The forecast models can give you probabilistic distributions of likely BZ outcomes. They cannot give you the actual value. This is why the NOAA forecast for June 3rd through June 5th predicts no G1 or greater geomagnetic storming. Not because the forecasters expect quiet, not because they are concealing a worse prediction, because the variable that decides the outcome is unpredictable beyond the most likely null outcome until the CMEs arrive at L1 and the spacecraft can read the field directly. Now, consider the additional complications layered on top of the basic BZ unpredictability for the June 3rd events. Complication 1. CME stacking. When 2 or 3 CMEs follow each other through the same solar wind channel within a short time window, the trailing events ride in the wake of the leading event. The wake is a region of reduced ambient solar wind density and modified magnetic structure. CMEs traveling through a wake can move faster than they would otherwise, can arrive closer together than their initial launch separation would predict, and can produce arrival geometries where multiple events are essentially crashing into Earth simultaneously rather than sequentially. The BZ pattern across a stacked arrival is the combined BZ of multiple clouds layered together. It can amplify southward orientations, or it can cancel them. The models cannot fully resolve which outcome will occur. Complication 2. The June 2nd filament eruption. We have already covered this. The slower filament CME is ahead of the faster June 3rd CMEs and will be caught and interacted with. The interaction will modify all of the arriving fields. The combined disturbance that crosses L1 will not be a simple summation of the source events. Complication 3. The partial northward deflection of the M7.7 CME. The deflection by the nearby coronal hole changes the geometry of how the eastern flank of that CME presents to Earth. The BZ pattern measured at L1 will reflect the geometry of the deflected flank, not the geometry of an undeflected frontal hit. That changes everything about predicting the impact. When you stack all of those complications on top of the baseline BZ unpredictability, you get a forecast environment in which the honest answer is nobody knows. Not because the forecasters are incompetent, not because the agency is concealing information, because the physics that determines the outcome is, by the nature of the system, observable only at the last moment. The forecast that predicts a most likely null outcome is the only forecast a responsible agency can publish given those constraints. And that brings us to the gap that almost every reader of space weather news misinterprets. The gap between 3 major flares, plus 2 confirmed Earth-directed CMEs in transit, plus a probable third, plus a colliding filament, and a forecast that predicts geomagnetic quiet. The gap between dramatic source events and a calm operational prediction. The gap that, when most people see it, triggers the conspiracy framing. There is a set of claims that circulates every time a major flare cluster fires from an Earth-facing region, and the official forecast does not predict catastrophe. Today's events will produce all of them within the next 12 hours. Let me walk through each one, and let me give you the mechanical reason why the claim does not survive contact with the data. Claim 1. NOAA is hiding the real forecast. The argument is that 3 major flares, 2 confirmed Earth-directed CMEs, and a possible third should produce a much worse predicted KP than 3.67, and the agency must be deliberately understating the prediction. The dispatch is the entire content of the previous section. NOAA cannot predict BZ. NOAA cannot fully resolve CME stacking. NOAA explicitly says in its publicly available discussion text that modeling of the filament CME interactions is ongoing. The forecast is conservative because the underlying physics is not deterministic. Conservative is not the same as concealed. If the agency were hiding the real forecast, the discussion text would not contain that admission. Claim 2. Region 4455 has the signature of an engineered event. Variants of this claim attach to any active region with unusual configurations. The anti-hail polarity, the continuous flux emergence, the 3-flare cascade. All of these, the claim says, are too productive to be natural, and some external force must be feeding the region. The dispatch is mechanical. Anti-hail regions are statistically rare but documented. They appear in approximately 3 to 5% of sunspot groups across a typical cycle. Their elevated flare productivity is a well-understood feature of solar magnetic dynamics. The sun produces approximately 4 times 10 to the 26th power watts of total radiant energy continuously. The largest terrestrial particle accelerators produce on the order of 10 to the 9th power watts. The gap between the energy a sunspot complex contains and the energy any imaginable terrestrial system could deliver to it is 17 orders of magnitude. 17 orders of magnitude is not a difference that engineering closes. It is a physical impossibility. Claim 3. The X 1.0 measurement is corrupted because of the GO-ES outage. We covered the GO-ES 18 to GO-ES 19 substitution earlier. The dispatch is operational. The 2 satellites carry essentially identical X-ray sensors, routinely cross-calibrated. The R3 classification of the X 1.0 is robust regardless of which satellite registered the peak. And the disclosure itself, NOAA explicitly noting in the public alert that the substitution occurred, is the opposite of a cover-up. An agency hiding bad data does not announce in plain text exactly which sensor it used and why. Claim 4. They're waiting until after impact to update the forecast. The claim treats forecast latency as evidence of concealment, that NOAA is sitting on a worse prediction and will only publish it once the storm is already arriving. The dispatch is procedural. NOAA's 3-day forecasts are issued on a fixed schedule and updated on event-driven triggers. The X 1.0 alert at 11:41 Universal Time was published in real time. The KP ceiling in the 3-day forecast will be revised in subsequent issuances as additional CME modeling completes. The X-ray alert came in minutes. The full propagation modeling takes hours. The next 3-day forecast will reflect that work when it is done. Claim 5. The sun is being weaponized to crash the grid. The argument is that sustained periods of elevated solar activity are being directed at terrestrial infrastructure for political or economic objectives. The energy budget physics from Claim 2 applies identically here. The sun is not steered. The sun's energy budget is so far beyond any imaginable human controllable system that the question of weaponization does not arise as a coherent physical proposition. You can run any framing that tries to fill the gap between dramatic events and a quiet forecast through this same mechanical filter, and the result will be the same. The gap exists. The gap is real. The gap is explained by the physics of what a space weather forecast actually claims, and the physics of what the underlying system can and cannot predict. The forecast does not look wrong because something is being hidden. The forecast looks wrong because most viewers have never been told what a space weather forecast actually claims. A space weather forecast claims a most likely outcome under explicit model uncertainty. It does not claim certainty. It does not claim that nothing dramatic will happen. It claims that, given everything the models can currently resolve, the most probable outcome over the forecast window is the published KP ceiling. The actual outcome may be higher. The actual outcome may be much higher. The actual outcome may also be exactly what was predicted. The forecast tells you the central tendency. It does not tell you the distribution tail. When you understand what the forecast actually claims, the gap stops looking like a cover-up and starts looking like what it is: a measurement of the limits of measurement itself. The agency knows what it knows. The agency knows what it does not know. The agency publishes both in the same document, in plain English, for anyone who reads past the headline number. The real question after the conspiracies are dispatched is not whether NOAA is hiding the storm. The real question is what you should actually expect over the next 48 hours. And before we get there, one more comparison always comes up when a major flare cluster fires. Whenever a major flare cluster happens, somebody invokes the 1859 Carrington event. The Carrington framing is one of the most common reference points for solar weather coverage, and it is almost always misused. Let me give you the actual numbers. The Carrington event was a solar storm that occurred on September 1st and 2nd of 1859. The British astronomer Richard Carrington and the amateur observer Richard Hodgson independently observed a white light solar flare visible through a telescope. Itself an extraordinary event, at 11:18 in the morning local time on September 1st. The flare came from a large sunspot complex with structural similarities to Region 4-455. Large area, complex magnetic configuration, productive geometry. The coronal mass ejection associated with the Carrington flare reached Earth in approximately 17.5 hours, a transit time so fast that it implies a CME velocity in the range of 2,300 kilometers per second or more. For context, the Type 2 shock velocity of the M7.7 on June 3rd was 313 kilometers per second. The Carrington CME was approximately 7 times faster. The geomagnetic storm that the Carrington CME produced had a disturbance storm time index, DIST, estimated by the Hayakawa et al. 2019 analysis at approximately negative 1,600 nanotesla. For context, a G5 extreme storm under the modern NOAA scale corresponds to a DIST of approximately negative 400. The Carrington storm was approximately 4 times more intense than a G5 extreme. The effects in 1859 included aurora visible across nearly the entire planet, including over the Caribbean and over Cuba. Telegraph systems across North America and Europe experienced widespread disruption. Telegraph operators reported sparks jumping from equipment, paper at telegraph offices catching fire, and the ability to operate telegraphs without battery power because the induced currents in the wires were powerful enough to drive the equipment directly. The Carrington flare itself was estimated by the Cliver and Dietrich, 2013. Reanalysis at approximately X45 on the modern X-ray classification scale. The X1.0 from region 4-455 today is, by the X-class numbering system, approximately 1/45th that estimated intensity, 45 times smaller. 1/7th, the CME velocity. The order of magnitude gap between today and Carrington is real, and it cuts both ways. Today's events are dramatic. Today's events are not Carrington. The frequency of Carrington-class storms is another part of the comparison that gets misused. The Riley 2012 analysis estimated a probability of a Carrington magnitude event in the next decade at approximately 12%, which extrapolates to a recurrence interval of approximately 1 per century. The Love et al. 2015 analysis revised those numbers and estimated a lower probability and a longer recurrence interval, on the order of 1 per several centuries. Either way, a Carrington event is a rare event. It is not a once-a-decade event. It is not a once-a-cycle event. Today is not that event. Today is a significant active period from a productive region during a normal phase of a normal cycle. The CMEs in transit will arrive over the next 2 days. They may produce moderate storming if the BZ orientation cooperates. They will not produce a Carrington-class outcome. There is a structural problem with invoking Carrington for every major flare cluster. It trains audiences in 2 opposite, equally harmful directions. The first is that audiences come to expect catastrophic outcomes from events that the underlying physics does not support. And when the catastrophe does not occur, they conclude that the warnings were exaggerated or fabricated. The second is that audiences become inured to the language of major space weather events. And when a true Carrington-class event eventually does arrive, and one will eventually, the language of warning is no longer believed because it has been overused. The triple flare cascade from Region 4, 455, is significant on its own merits without needing to be the next Carrington. The interesting story is the gap between 3 major events and a quiet forecast, not the gap between today and 1859. The triple flare cascade from Region 4, 455, is the 3rd major X-class cluster we have covered in the current solar cycle. The first was on April 24th, when 2 X-class flares fired overnight from a different active region. The second was on May 10th, when an East Limb returning region produced a colossal shockwave with a Type 2 shock velocity of 650 kilometers per second. Today is the 3rd. 3 X-class clusters in approximately 6 weeks is not anomalous. It is what a solar cycle in its late rising or peak phase looks like. The cycle's overall flare production has been elevated since late 2025, and the pattern of complex active regions firing in compressed time windows has been one of the dominant features of this period. Each cluster has had its own specific character. April 24th was a double X-class from a region that produced its events as it was rotating off the western limb, which created a CME trajectory question about whether the Earth-directed component would be revised upward. The May 10th event was from a previously unknown region rotating in from the far side of the Sun, with the far side helioseismic blind spot as the core mystery. We had only limited ability to characterize the region before its first major flare from the visible disk. Today's cluster has a different character again. The region is fully visible. The geometry is well characterized. The flares have been instrumented in detail. The CMEs have been imaged from 2 independent spacecraft. The forecast pipeline has had every input it could ask for, and the published forecast still cannot resolve what is actually going to happen. The uncertainty in today's case is not coming from missing observations or limited diagnostics. It is coming from the inherent unpredictability of the variable that decides the outcome. That distinction matters. The April 24th and May 10th clusters had observability gaps. The forecast uncertainty there could be partially attributed to limits in what the available data could tell us about the events. Today, the data is essentially complete by the standards of contemporary solar observation, and the forecast uncertainty is irreducible. We have all the information current diagnostics can provide, and the answer is still, nobody knows what BZ will look like at L1. That is the new thing about today. Not the number of flares, although 3 in 10 hours is on the upper end. Not the magnetic configuration, although anti-hail beta-gamma is exceptional. Not the CME count, although 2 confirmed Earth-directed events, plus a possible 3rd, is substantial. What is new is the convergence of complete observations with irreducible prediction uncertainty, openly acknowledged in the operational forecast text. This is the story that connects today to the broader arc of Cycle 25 coverage. The April 24th video discussed the trajectory reclassification problem, the way that an initial CME trajectory call can get revised as more data comes in. The May 10th video discussed the far side blind spot problem, the way that previously unknown active regions can produce events we have limited ability to anticipate. Today's video discusses the bees problem, the way that even with complete observations of a fully visible event, the decisive variable for impact severity cannot be predicted in advance. Each of these problems is a different way that operational space weather forecasting runs into the limits of physical prediction. None of them is a failure of the agency or the science. All of them are honest statements of what the underlying system can and cannot produce. And the cumulative story across the cycle is that the more carefully you read space weather forecasts, the more clearly you see that the forecasts are bounded by the physics, and the bounded forecasts are the ones that actually deserve trust. This connects back to the central thread of this video in a direct way. Today is not the first triple event of the cycle. Today is the first cluster in this cycle's coverage on this channel, where the forecast itself is openly carrying this much modeling uncertainty in its public discussion text. 3 scenarios are plausible for the arrival of the June 3rd CMEs at Earth over the next 2 days. The most likely scenario: 2 CMEs arrive between June 5th and June 6th. The M9.3 CME arrives first, as a partial halo with moderate plasma density. The M7.7 arrives shortly after, with reduced direct impact due to the partial northward deflection. The BZ orientation at arrival determines whether the combined disturbance produces minor G1 or moderate G2 storming, with KP values in the range of 5 to 6, or whether it remains substorm with only minor effects. Aurora is possible at high mid-latitudes if BZ turns and stays southward for sustained windows. Minor effects on GPS positioning, HF radio propagation, and possibly satellite operations within the envelope of routine operational management. The lower probability scenario: the interaction of the June 2nd filament eruption with the leading CMEs produces a compound disturbance with elevated plasma density, complex magnetic structure, and persistent southward BZ windows. KP briefly reaches 6 or 7. G2 moderate or G3 strong storming occurs. Aurora becomes visible to mid-latitudes, possibly as far south as the northern tier of the continental United States. Modest grid geomagnetically induced current effects appear in long transmission lines. GPS positioning errors increase. HF radio communication degrades or fails over wide regions. Noticeable and reportable, but within the operational envelope of contemporary infrastructure. The lowest probability scenario: the CME interactions amplify rather than disperse. The embedded magnetic fields lock into a sustained, strong southward BZ, and the arriving storm reaches G for severe or higher. This would require the interactions to add coherently rather than cancel, a window of coincident geometric alignment that current models cannot rule out but also cannot predict, and either a third CME from the X 1.0 or accelerated arrival of the 2 confirmed events. Probability is low. Probability is not 0. Operational thresholds for grid and satellite operators would be triggered, not a Carrington scale catastrophe. That would require another order of magnitude beyond G4, but a significant operational event. None of these 3 scenarios can be discriminated by current models more than approximately 30 minutes before the leading edge crosses L1. The DS-COVAR and ACE spacecraft will provide that final warning when it comes. Until then, all 3 scenarios remain open within the published forecast uncertainty. The practical takeaway is this: over the next 48 hours, watch the NOAA Space Weather Prediction Center alert feed. If a G1 watch goes up, the moderate scenario is becoming realized. If a G3 watch goes up, the lower probability scenario is becoming realized. If anything beyond that goes up, The lowest probability scenario is becoming realized. Aurora reports from northern latitudes will be the first public signal that B's has turned south. If you are in a location with dark skies and the latitude is right, the next 2 nights are worth checking. If you depend on GPS-based services or HF radio for any practical reason, build redundancy into your plans for the June 5th through June 6th window. Do not expect catastrophe. The probability does not support it. Do not assume nothing will happen. The probability does not support that either. Watch the alert feed. Read the discussion text when it updates. The deeper takeaway is what I want to leave you with. The gap between 3 major flares and a quiet forecast is not a cover-up. It is not a cycle anomaly. It is not the precursor to Carrington. It is the system working as designed, with its uncertainty named openly. The forecast you see is the most likely outcome under explicit model uncertainty. The agency that issues it has told you, in plain text, what it can and cannot resolve. The conspiracy framings that fill the gap when readers do not understand what the forecast claims are an artifact of misreading the document. The real question is not whether the storm will hit. The real question is whether you have learned to read a forecast that openly admits it cannot predict the variable that decides the outcome. Most viewers see a small KP number next to a list of dramatic source events and conclude that either the dramatic events are exaggerated or the small KP number is hiding something. Neither conclusion is correct. The small KP number is the central tendency. The dramatic events are the source data. The gap between them is the uncertainty distribution. Every solar cycle produces these moments. 3 major flares from a productive region, 2 or 3 CMEs in transit at the same time, a filament eruption set to collide with them, a forecast that predicts geomagnetic quiet because the variable that decides the outcome cannot be measured until it arrives. Most of these moments pass without incident. Some produce moderate storms. A few across the long arc of the cycle produce significant events. The cycle will eventually produce one that crosses into the catastrophic range. The question of which one is the question the forecast cannot answer in advance. The cascade fired. The CMEs are in transit. The sun is not finished. The forecast is honest about what it does not know. The next 48 hours will right themselves, and we will know, when L1 reads the field, what kind of arrival this was. Until then, the only honest summary is the one the agency itself has published. 3 major flares, 2 confirmed Earth-directed CMEs, a possible third, a filament collision in progress, and a KP ceiling that says, given everything the models can resolve, the most likely outcome is quiet, while the agency adds, in the same document, that modeling is ongoing. The sun fired. The plasma is on its way. The forecast is what it is. And the question of what happens next is, for the next 48 hours, suspended in the same physics that the sun has spent its entire existence enforcing, indifferent to whether the species watching it from one small planet learns to read the forecast correctly in time.